All right. Yeah, good evening, everyone. My name is Davey. I'm a product manager in the SDN business unit at Juniper. And today I'm going to talk to you about the Tungsten Fabric project, which is the open source SDN solution supported by Juniper and others in the community. Tungsten Fabric has a broad ambition of being a very widely applicable open source SDN solution. We don't want this to be kind of pigeonholed into one orchestrator or another. We want it to be broadly used in both private and public clouds, VMs and containers, and to deliver both connectivity and ubiquitous security. Some broad goals and lofty language on the slide, but hopefully after tonight's presentation you'll understand a little bit more about the way we try and deliver on that message. I'd be remiss if I didn't talk about first the code in the community, because if nothing else, I have two objectives. It's first to get you interested in the solution, interested enough to try it out and to use it in your own projects. And second of all, to get you even more interested enough to join our community, to participate as either active users, talking about your use cases and shaping the direction of the product itself and the project itself, and maybe even to contribute some code. Just to dispel a couple myths right off the bat, Tungsten Fabric and its commercial equivalent inside Juniper, CONTAINERIZED, is a completely open source project. So it's an open source core. The code is maintained in the community by the community, and Juniper is an active contributor. We brought our OpenContrail project, which I'm sure many of you are familiar with, into the Linux Foundation. And that, more than anything else, streamlined our governance and made it easier for the community to have an active role to ensure that Juniper isn't dominating the conversation one way or the other. Everything from our bugs to our blueprints is maintained in the community, so I encourage you to take a look at our blueprints in Launchpad to see where we're going, to participate in our Slack channels, and of course to jump in and join the community. We went through a little bit of a community reboot this year, so we're still trying to encourage folks to join that new rebooted community, and we really do want to emphasize that it isn't just Juniper and a couple other vendors or Juniper customers in the room. And yeah, check out our community online, our Slack channels, jump in, participate, ask questions. Just having more voices, more use cases, more input helps steer the project in a direction that's more broadly usable for the participants and your customers and projects. We have a very active community right now. We encourage a lot of the commercial Contrail customers to hop into the community as well. Obviously, a lot of SDN projects have stemmed from some early day lab efforts and some experimentation. We like to view the community around Tungsten Fabric as taking those lab efforts into the broader audience and having a kind of a more open discussion about what people are using SDN for in this day and age. More than anything, Tungsten Fabric and OpenContrail before it have demonstrated this steady progression, this push from labs and trials into POCs and then further on into production. And we've built out from kind of our platform, our fortress of private cloud and OpenStack to attack multiple different orchestrators to be more relevant in different use cases. And it all really did start out with telco, NFV, and service chaining. How do we replace those big monolithic appliances and create more software-driven services in networks? We didn't really appreciate maybe the grandiosity of the challenge, taking a fridge-sized appliance and try and boil it down into one or many more common off-the-shelf servers. So a lot of the early day development work around Contrail went into things like scale, performance, taking that centralized state that normally lives inside of our appliances or inside of our services complexes and distributing them out amongst the SDN control and data plane. From there, we started experimenting because tend to do a lot of work in the lab ourselves, with some of these new ideas that were bubbling around, things like containers and Kubernetes. And those slowly grew from POCs and just lab work into production-ready deployments. So with our 5.0 version of Tungsten Fabric, we now have kind of a strangely shaped solution, one that's good enough for distributing the workload of a gigantic network appliance across many virtual network functions, as well as a solution that's equally applicable to connecting fleets of tiny containers across distributed cloud resources. Tungsten Fabric aims to deliver so much more than just basic layer 2 and layer 3 switching. When we distribute our monolithic appliances out amongst many network functions, we need to provide things like effective and predictable load balancing. We need to provide distributed security policy enforcement, because we've just, by replicating our services infrastructure, we've made our attack profile much broader. So we need a way for our security policies to follow our workloads and to apply themselves where our workloads go. Analytics is a part of every single SDN solution. It's a huge part of Tungsten Fabric, so everything that we do needs to generate lots of telemetry and analytics information so that we can see our real traffic as it moves amongst all of these distributed workloads. Just because we're sharing flows amongst a set of 300 devices doesn't mean that we shouldn't be able to pick out one of those flows and get a great deal of information about it, right? We can't scale out our troubleshooting the way that we scale out our workload. So that still has to be very centralized and easy to query and troubleshoot. And of course, because ultimately everything that we do has to make its way from lab into production, we need the ability to do this all in a high availability, kind of seamlessly upgrading fashion. So for those of you who are not familiar with Tungsten Fabric, I figured I'd do just a brief update of what it is that we do and how it actually delivers value. So first of all, we've traditionally been a hypervisor-based SDN solution. We're now a hypervisor, container host, and public cloud-based SDN solution. And we build overlay tunnels, so we're an overlay SDN solution. We build overlay tunnels in order to ensure a clean separation of underlay and overlay state. It also means that we can dynamically shift around our service endpoints without wondering how the infrastructure is going to react to that. So we don't need to worry about things like convergence as we move workloads and services through our various data centers. Instead, the overlay keeps track of where the service is and directs the traffic there. The other kind of interesting thing about Tungsten Fabric is that we're a flow-based or flow-aware SDN solution. So we keep track at a very granular level of all of the types of flows that are coming into the interfaces that connect to VMs and containers. Now the important thing about that is because we have flow awareness, we can do things like flow validation to make sure that these are flows that are conformant with our security policies. We can do very rich load balancing that's done in a resilient fashion, so we'll map flows into a services complex and we won't move those around if we scale in or scale out our services complex. How that really works in a specific scenario, I always beat up on the 3-tier app because I think the 3-tier, the web app and DB is a really common framework to visualize the impact of SDN. First of all, because Tungsten Fabric acts as that first hop forwarder in an orchestrator container solution, that really means the VMs and containers plug right into our VROUTER component. So that means any traffic, whether it's going to an adjacent web server in the same network or into a different virtual network, we have that same ability to control the flow of traffic and enforce security policies. And that lets us achieve microsegmentation by applying security policies even within the same virtual network. And that prevents the spread of, say, malware or just configuration mistakes, really constrains the blast radius of an individual service. So we can make sure in the case of my completely contrived 3-tier web app, example that my front-end web servers in the green virtual network can't communicate amongst one another. Now, as I'm moving traffic through my virtual networks, as I'm sending traffic to my app backend, I also have the ability to enforce security policy. So I can again say through network policy that these two virtual networks should be able to communicate with each other. That's all well and good, but by having that full flow visibility, I can then secure that traffic to ensure that only the application traffic itself should be forwarded. Finally, when we're moving traffic between virtual networks, we're not a typical longest prefix match router. Instead, we can override those forwarding decisions and reroute traffic to special instances, our virtual network functions. And this is the typical service chaining example where we say we override the routing table to steer traffic through a firewall before we let it go between virtual networks. Because we're using the SDN controller to make this decision, we can scale in and scale out our firewall services complex, and the SDN controller and the data plane will be responsible for making those load balancing actions. Find me the right healthy firewall to send this traffic to, and it'll sort out the rest. What's critical, and why I started out by saying overlay-based SDN solutions, if we look at that big jumble of compute resources that's underpinning all of this, we didn't really need to worry about which container host or hypervisor is running our workloads. Instead, we let the orchestrators place that workload on the most optimum compute or container resource, and the SDN controller keeps track of where those resources are supposed to be running, instantiates their virtual networks, applies their security policies, and then forms the overlay mesh. So your data center can start moving back to a more traditional style of purely routed set of simple devices, or even if you want to go totally wild, just VLAN 1 everywhere, right? We don't need to worry about a lot of complexity or state in the underlay. Instead, we can contain that all in the overlay. What this gives us, especially in modern application deployments, is the ability to completely abstract away from the underlay. That means that we're not talking about a set of switches and routers anymore. Instead, we're talking about maybe a set of internet links. As I start moving my containers into AWS or GCE, I don't need to worry about what compute host is running my virtual router data plane. Instead, I just need IP reachability. So again, it reduces the requirement for connectivity and delivery of services to just being able to ping the far end host, and the VROUTER data plane looks after the rest. Again, as my workloads move around, my security policies move around, so I don't need to worry about putting a lot of state and security into my public cloud infrastructure. I just need to make sure I treat it like my underlay, make sure that all the endpoints can talk. Just blowing out the architecture of Tungsten Fabric for a second, we have the traditional SDN-like architecture of a separated control and forwarding plane. So in the middle is our controller infrastructure, a high availability cluster that runs our configuration, analytics, and control plane. Speaks a set of traditional networking protocols. With a Juniper person on stage, I'd be remiss if I didn't say it runs BGP. It runs BGP to interface with external networks, for example, to advertise connectivity, as well as it can offer up BGP to workloads. That's not really the important part. The important part is that it speaks the same set of protocols that your data center and edge firewalling infrastructure speaks today. So there's no new encapsulations or different protocols that you need to speak to interface with the controller. Focusing on the data plane for a second, in each of the compute or container hosts, we run a VROUTER data plane. And this replaces a lot of the internal machinations of the hypervisor or the container host. Things like Linux bridges, the traditional routing stack, IP tables. All of these functions are still there, but just not used by VMs and containers that are connected to Tungsten Fabric. Instead, we look after all of the forwarding and security policy application. And the vRouters themselves communicate with the controller using XMPP to download all of that virtual network configuration and security policy information. Kind of used as more of a rich update mechanism than BGP. We can't speak BGP everywhere. Believe us, we've tried. To the actual developer, so what do we expose to our end users and customers? Obviously there's a UI. There's also a set of REST APIs that you can use to programmatically instantiate connectivity. And then depending on the orchestrator that we're running in, we expose Heat APIs. We'll listen for Kubernetes API calls. So we'll react to the orchestrator as well and expose a set of native APIs for the orchestrator to instantiate connectivity and security policies. I wanted to drill down for a second on that data plane element because I think it's really powerful that we have a software accelerated data plane living inside of each one of these hosts. This is what really lets us control the flow of traffic to apply security policies and to establish those overlay tunnels. This is really what makes it work. But obviously, there's no one-size-fits-all when you're attacking both container workloads as well as virtual network functions. We need the right way to deploy the VROUTER to address each of these scenarios. So the first is cheap and cheerful kernel mode forwarding. Works great in the public cloud, works great with containers, and very few modifications required to run the kernel module. Basically, we leverage DKMS to get the right kernel module for the version of kernel running on the actual host. We insert that kernel module, and then you're off to the races. Contrail can then communicate with, or pardon me, Tungsten Fabric can communicate with the control plane and instantiate all of the virtual networks required for that individual host. That doesn't quite cut it when we're dealing with tens of thousands of connections per second or multiple gigs of throughput. In that case, we need something like DPDK to allocate dedicated forwarding CPUs to give us that closer to hardware deterministic forwarding profile. DPDK has done a fantastic job of exposing accelerated networking to virtual guests, but we are always in a bit of an arms race with the application and service owners who want to drive more bandwidth, more connections out of the same set of hardware. Right now, our go-to mechanism for that is by exposing SRIOV virtual functions to high-performance data plane guests. But again, not every guest in a deployment is going to be high performant or need that high performance data plane. So for lower speed interfaces like signaling, management, basically anything that's not in the direct path of the subscriber service, we can still leverage the SDN features that we lose when we use SRIOV. And yeah, sorry, I should have called that out quicker. When we use SRIOV virtual functions, we're of course bypassing everything in the kernel. That means, or kernel and user space, going right to the hardware, which means we don't have any of those SDN features anymore. We need to make that up some other way. Thankfully, a lot of our data plane instances are quite simple. So in some cases, we can get away with it. In other cases, we're back to our original way of solving problems with lots of complexity and state in the underlay. Finally, something that we're working with folks like Intel as well as other hardware vendors is the FPGA accelerated SmartNIC topologies, deployment modes. And this is where we gain the best of both worlds. We have almost direct access to the hardware from the virtual guest provided by the SmartNIC or FPGA accelerated interface. But we still get access to that SDN overlay with the actual data plane of the SDN solution running inside of the FPGA. This is an area of active development right now, both inside Tungsten Fabric as well as elsewhere. Focusing on containerization, because this has been a hot area of development for VROUTER, and just like the previous discussion about accelerating sidecars, there are real needs to deliver highly performant networking into a container environment. Right now, a lot of the reasons to deploy SDN in containerized environments is agility, flexibility, mobility. As our container workloads move around, we don't need to worry about updating our underlay. We don't need to worry about adding more state to the network. Instead, the SDN just looks after that for us. As we start bringing these solutions out into production, we're going to have more and more requirements for high-performance containers, and that's where we can leverage a purpose-built data plane like Contrail to give us both the flexibility of SDN but the performance of a production-ready data plane. So in a Kubernetes environment, the VROUTER runs on each of the container hosts. It provides all of the traditional pod networking, actually deployed without any configuration. It looks and smells like any other CNI solution. What it offers is that, first of all, overlay topology hiding. So we don't need, or pardon me, underlay topology hiding. So we don't need to worry about all of the switches and routers that our container hosts connect to. Instead, we can use our Kubernetes manifests to specify connectivity and security requirements. It also provides all of those kind of telco-esque features that we've relied upon when we're scaling out virtual network functions. Things like reliable load balancing become absolutely essential as we're distributing our application using Kubernetes. One critical element to the Tungsten Fabric Kubernetes solution is that we implement the network policy framework. So you can use Tungsten Fabric to control the flow of traffic into and out of your container services in both ingress and egress directions. So this, more than any other reason, if you're looking for a reason to play around with Tungsten Fabric in Kubernetes, if you're looking for something that can implement network policy and provide overlay tunneling, this is a fantastic reason to kind of take a look and see what the solution looks like. One element of the solution I didn't really harp on a lot about and didn't feel really relevant, I guess in retrospect it does now, is that Tungsten Fabric is fully multi-tenant. So for every tenant or project, traditionally inside OpenStack, but now just generally, we would create a set of virtual forwarding and control plane partitions, so that all of the reachability information, all of the security policies for an individual tenant are completely isolated from any other tenant. This becomes really useful in either multi-tenant Kubernetes environment where we're providing, say, like a platform as a service to multiple departments or even multiple customers. Also, it acts as a really great guardrail if you have multiple deployments in your environment to ensure that one can't muck about with the other. The traditional way of achieving this in Kubernetes is using namespace isolation. I always like to think of namespaces as more like folders in a file system than the brick wall surrounding, or the walls and the moat surrounding a castle, right? It's really meant to allow you to have overlapping resources. It's not meant to create isolation between those resources. So my Kubernetes namespace lets me have two services called web, but they can communicate freely amongst each other. And if I want to prevent that communication, I need to use something like security policies or firewall rules. In the Tungsten Fabric solution, we have the ability to create custom isolation based on tenant policies. So we can say, for example, just a really easy and convenient way to create multi-tenancy. Every namespace now creates a new tenant. Every namespace creates a new fully isolated partition. So now that namespace kind of acts the way I think we all expected it to. If I place two things in two different namespaces, they cannot communicate between each other unless I allow it via policy. That's not security policy, it's not a firewall sitting in between them, that is actual network reachability policy. And then I can further use my security policies to isolate those workloads or control the traffic going into and out of them. So that was just a brief overview of kind of what we've been working on, where we are today, and what we can do. I'm going to spend the rest of this presentation talking about what we've been up to. So what's coming in the latest release of Tungsten Fabric. The first thing is we took care of a little bit of technical debt that we've been holding on to since our 1.2 release. We completely redid our architecture to move all of our critical components into containers and adopt a microservices architecture. The reason that we did that was to give us better deployment, more access to deployment frameworks, as well as more predictable deployments and easier lifecycle management. In the containerization space, a huge focus for us in this release was the implementation of a rich network policy. So we have the ability to provide ingress-egress network policy, as well as flexible selection of ingress controllers. So you don't have to take the HA proxy that we ship out the door. You can swap out HA proxy for Nginx or for traffic or for whatever project that you like. F5. And then on the NFV front, we've been challenged by a lot of the carriers to talk about how we can now realize the NFV ambitions that we've all been talking about for the past couple of years. Virtualized evolved packet cores have been in lab trials and deployments for a couple of years now, and are slowly making their way out into production. And now we're starting to be faced with the challenge of, well, how do we actually get production traffic through this instance? How many of these instances do I need to achieve my traditional subscriber level? It's one thing to say that we can just scale out more and more instances, right? And that's totally fine. We can have 255 servers performing a job, but we need to make sure that we're getting the most out of those servers. It can't be kind of a linear scale, or else this whole thing, the CapEx numbers just don't make sense. So the first thing, starting with kind of the boring stuff first, the containerization of the Tungsten Fabric control plane, the adoption of microservices. This was a huge effort for us. It wasn't necessarily exciting. It doesn't expose a lot to the community right away to play with, but it was really important because it lets us move forward faster. By shipping our components in containers, we no longer have that whole dependency issue that complex software deployments have. We don't need to tell our users in the community that you need these X number of packages at this specific version in order to deploy the software. Instead, we can ship that all as one atomic container or set of containers, and keep all of that complexity inside of the container images. The other neat thing that we can do is, once we're inside of a container, is we can benefit from container orchestration. So we can plug the Tungsten Fabric control plane into Kubernetes, kind of a Kubernetes on Kubernetes style of deployment, to make use of things like rolling upgrades and rollbacks and staged rollouts. And that just makes the management of a complex system much easier. It also means that we have that big rollback button. If a software deploy does not go well, we can rip the entire environment back to the previous known good version. We also have much better tools to work with containers. We can plug into a lot of neat frameworks like Docker Compose and Kubernetes Helm charts to give a much more scripted deployment experience, and one that, again, kind of doesn't expose as much risk to the operators who are deploying it. We've adopted Ansible as our kind of de facto or our default deployer as well. So the goal is to take that Tungsten Fabric deployment experience and really boil it down to the most simple set of primitives possible, and to make it as easy and fast and replicatable as possible. And time permitting, I'll show a resource at the end that everyone can take a look at if they want to try and test drive this and kind of benefit from these efforts. I've been kind of dancing around this point. I don't feel like I've made it very well, so I apologize. But the two different phases, the two different types of deployment in a typical Tungsten Fabric scenario are really big. These are the virtual firewalls that sit in front of the mobile services complexes at all the mobile vendors across the US and Europe. These could be the organization firewalls. Gigantic, what used to be gigantic campus firewalls are now virtual instances running in servers. These have very different requirements than the managed containers running inside data centers and public clouds. So really we need a solution that exposes that same common set of network behaviors and primitives across both of those environments. The way that we've done this is by exposing a common set of security primitives and frameworks from Tungsten Fabric. So we want to try and take the security out of the underlay, out of the edge, and out of the middle boxes, and put it into the SDN solution, so that the infrastructure, the data center switches and firewalls or public cloud gateways don't need to have as much service state so much as they need to just permit two things: communication between all of my compute resources and access into the actual services themselves. Nothing about any of the transactions between the apps in the middle, and nothing certainly that should change as I scale in or scale out my deployment. So obviously in OpenStack, we have made extensive use of security groups to provide distributed stateful firewalling for all of our OpenStack instances. In Kubernetes, we've now adopted network policy as our way to expose that security framework. So you can again take the security policy for your workload, attach it to your Kubernetes manifest, and that will instantly turn that VROUTER in the container host into a stateful firewall. So now I don't need to have a gigantic stateful firewall sitting in front of all of my workloads. I can have that distributed across all of the vRouters, instantiated whenever a workload is. Of course, we work with other orchestrators like Mesos as well. And we have a netconf transformer that can even transform those firewall filter, or in those security policies into firewall filters applied to bare metal switches. The goal is to have a single programmatic API for you to push your policies into, and it'll just follow your workload, those policies will follow your workload around as you move them from cloud to cloud, container to VM, or even connect them to different bare metal switches. On the other side of the spectrum, we have the virtual network function enhancements. So a lot of this is being driven by VPC. A lot of the vendors that we're working with are still struggling with the challenges that come with delivering high subscriber counts and high throughput entirely in software. The go-to answer for this is to leverage SRAOV virtual functions to connect those service functions into physical networks. So you just bypass all that software mess in the middle, let the traditional switches and routers handle it. We don't need to worry about scaling our software as much. The downside, of course, is now we lose all that magic of SDN I've spent the last 20 some odd minutes talking about. We don't have load balancing, security policies, or that programmatic instantiation of networking. So now I have to deal with it again. I'm logging into switches and routers and firewalls, and I don't want to do that anymore. For the brave few that have stuck with us along this journey, we've managed to profile their workloads, to optimize our forwarding, and across our 3 major versions, we've demonstrated a 3-time improvement of flows per second, or connections per second. This is completely aside from any other work we've done. This is just raw optimization, not new features, but really just improvements. Now, there's only so much you can optimize before you start getting diminishing returns. And really, when we look at the problem of a traditional we'll call it service head-end instance, like a PGW, or even a gigantic firewall, there's not a lot of actual fine-grained state or subscriber information required. So what happens if we start ignoring some of those granular details? That's what we call a fat flow. Right at the edge of our solutions, our service stacks, whatever we're delivering using our SDN, I need to know everything about the flow so that I can do things like load balancing, I can do security policy enforcement, I can even traffic steer that into certain service instances based on that flow information. At the service instance, I don't care as much about the individual sources or destination or source ports. I have macro actions on those instances. I take traffic in from one side, I fire it out on the other side. There is some logic in that service instance that controls what happens in the middle, right? But the SDN at that particular instance doesn't care. So this is where we have this ability using fat flows to selectively, on a per interface or per instance or even per tenant basis, control how much we care about flows. The previous way that we did this was by masking off certain elements of the flow mask. So we could ignore things like the destination port. But it really wasn't as granular as we'd like. With the new fat flow enhancements that came in Tungsten Fabric 5.0, we now have the ability to mask off pretty much any part of the 5-tuple or disable flow-based forwarding completely. Now, as with everything, there's always a trade-off, right? If we turn off flow awareness, we lose a lot of analytics and insight. We don't get an analytics record anymore for every flow, so our network could be harder to troubleshoot now. We also can't perform granular traffic steering because we don't have flow awareness anymore, so we can't say this flow goes there versus that flow goes here, right? That's really it for me. That's my gigantic big improvements for VNFs, my tiny small improvements for containers. What I wanted to end this with was kind of a call to action. through that containerization and lifecycle automation improvement that we've done, we now have the ability to throw up a Tungsten Fabric demo in about 10 minutes on an AWS, or if you point your AWS account at this automation script. Please check it out. Try out Tungsten Fabric. It by default deploys I think it's a 3-node Kubernetes install with Tungsten Fabric. So once you run through the automated installer, you can just start throwing manifests at it and see what your workloads look like with an SDN overlay. So check it out, jump on our Slack, join our community, tell us what you thought about it and how we can improve. There's the QR code. Please go test drive Tungsten Fabric, give it a shot yourself.